That's it.
Oh, there's a mic. Okay.
Yeah.
Should I be using this?
You should use it.
Yeah, sure.
Yeah. Okay. Welcome everyone here. It's my great pleasure to host Edmund here. You can call him Ed.
Yes.
So a bit intro for him. He's my academic brother, so we studied undergrad together and then graduated under same supervisor. So we are actually academic brothers. Okay, actual brothers, same father, right?
Yeah, same father. Yeah, of course.
Okay, so huh? Yeah, so yes, so after graduation, I came to SMUM, so he went for IHES, and then after about 3 years, and then he was based in Sydney now, University of Sydney, so back to Australia. We were in Canberra last time. Yeah, so he will tell us about fusion categories and Coxeter theory. Okay, pass the time to him.
Okay. Oh, thanks. Can you hear me now? Okay. So thanks a lot for the invitation and also like the introduction. It's good. It's a great pleasure to be back in Malaysia. Sunny and potentially too hot and humid for me, but it is what it is. So today I'll be telling you a little bit about fusion categories and Coxeter theory, which are, I guess, a priori kind of unrelated topics. And the goal for my talk today is to tell you how they're related. And it turns out that the way that it all started really is just from a numerical coincidence. So a lot of interesting mathematics came from numerical coincidence, and I would like, or at least I would hope that this is also one of the cases where it will become an interesting mathematics. Although a lot of things are still work in progress, but today I'll tell you where the starting point is. Okay, so let me begin with the following schematic diagram, if you wish, which has a lot of mathematical topics, and everything are somehow related or have some sort of classification that appear where the diagrams in the middle would appear, which are all what we call ADE thinking diagrams. Hopefully you've seen at least one of them before, and hopefully you have at least touched or learned one of the topics that surround all these kind of diagrams. And the reason why I really like this picture right here is the fact that, again, it relates a lot of different mathematics to one another. Okay, whether or not you're studying algebraic geometry, maybe you're interested in Mackay correspondence, or maybe you're more algebraic, someone like me, you'll be interested in quivers, and they're all related via thinking diagrams, in the sense that every time when you want to study some sort of classification problem, these diagrams would appear. So for today's topic, I kind of want to talk about something slightly more general, which is living in the bottom right corner right there, which are what we call Coxeter groups. So while groups are certain groups which control root system coming from Lie algebras, sometimes also related to quivers, depending on the point of view. And Coxeter groups are certain slightly more general families of them. Okay. So let me just quickly define for you what Coxeter groups are. So first of all, they are quite easily defined because they're just going to be given by generators and relations. And they are just defined from what is called a Coxeter graph. Okay, so something very combinatorial. The Coxeter graph is just a simplicial graph. By that, I just mean that you have vertices, you have graphs, and between every two vertex, there's only one edge that connects them. Okay, simplicial graph, and I'm allowing labels on the edges of my graph. Okay, so it can be labeled by numbers either 3, 4, 5, so on and so forth, natural numbers greater than or equal to 3, and also including the infinity label. Right? Given such a graph, I'll just define the Coxeter group, and it's going to be defined as follows. So the generators of my groups are given by exactly the vertices of my graph. So for each vertex in your graph, you're going to get one generator. And the relations are as follows. Every generator is going to be an involution. So what I mean by that is that the square is going to be the identity. And moreover, they satisfy the relation that's looking like this alternative relation that says ST, 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 blah, 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 is equal to TS, 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 blah, blah, blah. And the length of those alternating relations is given exactly by the label that connects the edge. Okay, so just by convention, if two vertices in my graph are not connected by an edge, MST is equal to 2, so they commute. And otherwise, the grading relation, so the alternative relation that you have there is exactly equal to the number that you have. All right. Okay, so just finally, just one small comment. If MSC is equal to infinity, then by convention, we'll just say that there's no relations between them. Okay, so this seems pretty abstract. So let me just give you a few examples so that you have something to keep in mind. Doesn't need to be connected. So I'm not assuming irreducibility for that. Indeed, I guess all the examples I'm giving you are connected, but it doesn't have to, for the time being, it doesn't have to be connected. Okay. All right. So the first example right there is just the A3 graph, which has exactly 3 vertex and just 2 edges connecting all the 3 vertices that you see up there. And that group right there. So if you take this graph right here, and you write down what the Coxeter group is, you get exactly, well, 1 generator for each vertex. So we have S1, S2, and S3. And then the relations are exactly the following, right? So S1 and S2 will break because S1 times S2 times S1 is equal to S1 times S2 times S1. Okay, so that's the braiding relation. And similarly for S2 and S3. And if you write down this group presentation, what you get is exactly the symmetric group. Okay, and how do you think of it as a symmetric group? You just think of S1 as the transposition that swaps 1 and 2, S2 as the one that swaps 2 and 3, and S3 as the one that swaps 3 and 4. Okay, so that's the symmetric group. And the other group, maybe slightly simpler, is probably the second group right there. And it has exactly 2 generators, S and T, and it's labeled, the 2 vertices are connected by a label M. So what that means is that if I take ST to the power M, I get exactly the identity. Right? And this is exactly the group presentation for the dihedral group of 2M elements. Or if you want, the way that I will say it is that it is exactly the isometry of an M gun. Okay, so in particular, S is a reflection, T is a reflection, they are adjacent reflections, and S times C is a rotation, and that rotation has exactly M order.
Sorry, I thought M means like ST, 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 M times EST, ST, M times.
Exactly, great catch right there. So I played a sleight of hand, if you wish, by using the relation that S squared and T squared is equal to 1. So do I have a pen? Maybe I can do it here. So let me just do this. STS equals, can you see my writing there in red? Not quite, right? Is green better? It's okay. Let me just write on the blackboard for now. So can you see this STS?
Yeah.
Great. STS equals TST. And let me convince you that, so what can I do? I can multiply T on both sides. So that gives me this. T squared equals 1, so that cancels off. And then if I repeat this, I'm going to get ST cubed equals identity. Okay, so I've played the sleight of hand there. And exactly, so you're right. Cool. Are we happy with that? All right, so I've given you 2 examples. The first 2 are finite groups, right? Because the isometry of M gun is a finite group. The symmetric group, so permutations of M elements is also a finite group. And then the last example here is just PSL to Z. If you don't know what that is, the point is just that is an infinite group. Okay, so you have graphs, you have a Coxeter graph, you can define a group out of it. And these families of groups consist of finite groups and also infinite groups. And in 1932, Coxeter, who first studied this kind of group, already gave an interesting classification for this kind of group. And what I mean by that is that Coxeter in 1932 managed to classify all of the finite Coxeter groups. So if you write down some random graph, these are exactly the Coxeter, the finite Coxeter groups. And just to go back to your question there, I'm assuming irreducibility here. Okay, so you can take any products of these kind of. So if I now just take unions for any combination of these graphs, they will all still be finite groups. Okay, so Coxeter, to be more precise, Coxeter has classified all of the irreducible finite Coxeter groups. And the theorem says that the Coxeter group is finite if and only if the Coxeter graph looks exactly like one of these graphs right here. Okay, so if you've seen ADE diagrams before, it consists of the ADE sum as well that you may be familiar with. And on the 3rd row right here, this is also probably something slightly more familiar to you if you're allowing yourself to study non-simplest Lie algebras. Those are also included. And perhaps the weirder guy is the very, very last row here. sometimes also called the non-crystallographic Coxeter groups for that reason. Okay, so everything first, second, and third row are all Lie algebra type, if you want, or Lie group type, and then there's also the non-crystallographic types at the very end, including the dihedral group that we saw just now. Okay, sorry, the H non-crystallographic, non-crystallographic. Okay, any questions up to now? All right, if not, then let me go back to this picture, right? Sorry, it has moved on my iPad, but not yet on the screen. Ah, there we go. Okay. So let me go back to this picture right now. I'm sorry that you can't really see the arrows, but my point here is really the fact that I'm interested in solving problems about Coxeter groups. Okay, and the diagrams that you've seen, so the one in white color that connects Weyl groups, only allows me to solve problems involving Weyl groups. So if you want any kind of tools that borrow from other mathematical field, reverse Lie algebra, cluster algebra, or Mackay correspondence, only allows me to say something about Weyl groups rather than Coxeter groups. And my main goal, my general goal, is to somehow really enhance this whole picture right here so that everything is complete, at least with respect to Coxeter groups. What I mean by that is that if I want to study Coxeter groups, I can also jump to quivers, study something about quivers, and then solve some problems about Coxeter groups again. Okay, whereas previously, if I can only solve problems about Weyl groups because I can only jump to actually just quivers, and then when I go back, I'm only obtaining Weyl groups, not Coxeter groups.
Going back is not easy.
Exactly, going back is not easy, and part of the goal is to show you how to go back. Okay. So here are the goal of today's talk. I'm going quite slow, but I think. So the first goal is to somehow tell you something about Coxeter groups, which in fact trying to study them as reflection group on lattices, which are no longer just integers. Okay, so usually when one says what a lattice is, it will be a free abelian group rather than a free module over some weird ring. Okay, so I'm going to try and convince you that actually doing this is a sensible thing to do because these kind of rings, which I call fusion rings, have nice integral properties, which helps with a lot of things that we want to do. So that's the first part of my talk. And then I'll tell you something about the corresponding quiver theory. If you want, this is building the theory on the quiver side, something slightly more general, and then showing you how to go back as well. All right, and if time allows, then I'll talk about something in relation to K-Taiwan conjectures. Okay, so that's the goal of today's talk. Any questions before we jump into the first part of my talk? Nope. All right, let's move on. So let's go back to the following picture and look at this particular example, which is the isometry of the pentagon. All right. So if I want to look at the linear representation of this pentagon, what do? Well, I really draw the pentagon and then I draw out all of the reflection lines, and that tells me a linear representation, right? Because reflecting along this line, reflecting along this line maybe, will generate a group. And I've written down something in R square, therefore it's a linear representation. And moreover, this representation is faithful. Okay. So to be slightly more precise, what do I have to do? I'll have to pick, if I wanted to reflect along S, then I'll have to pick a vector that is actually orthogonal to it, and also orthogonal to T. Okay. And what do we see in relation to these two vectors? Again, I apologize for the colors not showing up. So maybe let me try and draw something out. There we go. I have a vector alpha S here. I have a vector alpha T here. And for this to be a representation of the isometry of the pentagon, these two vectors have to form an angle of pi over 5. Right? Otherwise, the reflection lines wouldn't have the correct angle. Okay? So what does this say about my inner product? So my inner product has to look as follows, right? The inner product between alpha S and alpha T has to return the number negative cosine pi over 5, right? Because the projection down has to have cosine pi over 5 length, and then it's in the other direction, therefore it has negative. Okay, so that's what the dot product should return. All right, and moreover, if I wanted to write down the reflection along S, what do I need to do? Take any vector that you like, project it down to this line here. That gives you this vector here, and then just do 2 copies of it, right, in the opposite direction. That's exactly the reflection, right? So project it down to the line, the alpha S, and then do negative 2 copies so that it goes onto the other direction. Are we all happy with this? All right, and so if you want, the formula right there is really just the following. S acting on the vector V, all that it does is just take the vector V, projects it down to the alpha S direction, and then do negative 2 copies of it. And that's exactly the reflection along S. Similarly with reflection along T. Okay, so let me just again do a sleight of hand so that I can absorb the number 2. And the formula that I have is exactly the following. If I wanted to take S acting on V, then it's just V minus alpha S times V as an inner product. That's a scalar now, and I'll extend that with respect to alpha S. Okay, so I've just really just absorbed the number 2 into my inner product. Okay, and as it turns out, this intuition, if this geometric intuition turns out to work in general. And what I mean by that is the following. So now take any random Coxeter graph, right? Any Coxeter graph, your favorite choice. I can write down the following symmetric bilinear form, which essentially does what we saw just now, right? If my two vertices are connected by an edge labeled by MST, then I just want their inner product to return the number negative 2 cosine pi over MST. Okay. So just now we have so let me go back to my picture here. Just now we have exactly S and T connected by the number 5. So their inner product, so alpha S and alpha T, returns negative 2 cosine pi over 5. And now we'll just generalize this and do it for all possible Coxeter graph. Okay. So this currently is just some random bilinear form, symmetric bilinear form on the vector space. Okay. And the theorem or definition first defined by Jacques states that in fact this is, if we do exactly the same construction as just now, the S acting on V, which is V minus the bilinear form of alpha S and V multiplied by alpha S, actually is a faithful linear representation of my Coxeter. Okay, and this is usually called the Tits representation, or sometimes also called the geometric representation as well. Yep.
Alpha S is like, it's also orthogonality thing. What's the connection between alpha S and S?
So for every S, you create a basis element for the vector space.
I see. So it's just like something that's arbitrarily decided.
Yes, exactly. So if you want, let's go back to this picture again. So this Coxeter graph has exactly 2 vertices, and my representation has exactly rank 2. Okay, so the basis element for my vector space is exactly given by the number of generators in my Coxeter group, or the number of vertices in my Coxeter graph.
Okay.
Yes. So more precisely, what this statement really says, what Jacques has really proven, is that every Coxeter group of rank n, and by rank I just mean number of vertices in my Coxeter graph, has exactly a faithful representation equal to the rank. Dimension equal to the rank. Okay. All right. So again, let me go back to the smallest example because it's much easier to write down. If we look at all of the possible dihedral groups, so they are all just the Coxeter graph with 2 vertices and 1 edge labeled by M, then the linear representation looks exactly like the following. In particular, if you look at the 2 matrices right there, those are the matrices for the linear representation with respect to the basis alpha 1 and alpha 2. Okay. And basically, what Jacques has proven is that this is a faithful representation of my Coxeter group. Right. And for this particular example, it's quite easy because this really is just what you would imagine the isometries of an M-gon would look like. Okay, so now here's the question for all of you. Suppose that I just want to solve an equation, like a student, if you wish, and just say that now I don't know what to do with this number 2 cosine pi over m, and I'm just going to chuck in a variable x right there. Right? So what is the condition on x? There are these two matrices, right? Previously, I had the number -2 cosine pi over m sitting up there. I go back again. Right? I had the number 2 cosine pi over m sitting up there. And now I'm just replacing 2 cosine pi over m with this variable x. And I'm just asking you what condition on this variable x such that my order of my element S1 times S2 previously has order m. So now I'm asking you what kind of conditions I have to put on this variable x so that the order stays the same. Okay, so this is some sort of algebraic condition if you want.
Just like
yep,
calculate, get some degree f polynomial.
Exactly. So you calculate, you just do your calculation, and then it turns out that it's completely controlled by one kind of polynomial, a degree m polynomial called the Chebyshev polynomial. Okay. If you've seen quantum numbers before, this should intrigue you because this is also the quantum number of m, the mth quantum number. If you don't know what that is, completely ignore me. And the point is just that these kind of polynomials satisfy a recurrence relation that is defined as follows. The 0th degree polynomial is just equal to 1. The first degree polynomial is just equal to x. And then from there on, it just satisfies a recursive relation that says that the k plus 1 degree polynomial is just x times the previous one minus 2 steps of the previous one. Okay, so just this. Oh, come on. Just this equation right here. Okay, so k plus 1 polynomial is exactly just x times the kth polynomial minus k minus 1 polynomial. Okay, so I've written down a few examples. The second degree polynomial is just x squared minus 1. The third degree polynomial is just x cubed minus 2x. And as it turns out, if you just do this calculation, this exercise, you can prove that S1 times S2 has exactly order m if and only if x satisfies the Chebyshev polynomial of m minus 1. Okay, for the lowest m, because otherwise you get something which, of course, still goes there identically, but the order is not actually the right one. Okay, are we all happy? So of course, I didn't really do the calculation yet, but I urge you to do this exercise at home. And if you're wondering why did the 2 cosine pi over m number actually worked, the point is that this Chebyshev polynomial contains the minimal polynomial for 2 cosine pi over m. And in fact, it's the unique polynomial that contains all the possible roots, which looks like 2 cosine k pi over m for k the correct range of numbers as well. Okay. So in other words, let me rephrase things slightly now. Instead of taking my representation to be over the real numbers, I can just replace it by the following ring. Right? I'll just take the polynomial ring Cx, mod out by my Chebyshev polynomial of n minus 1 degree. Okay? And I'll write down these two matrices here. Okay? So the condition, the computation that we showed just now, it has order m, proves exactly that this is a faithful representation of our dihedral group. Okay. Usually, the TITS representation was a linear representation, and by that we mean that it is linear over the real numbers. Now this is linear over that ring Rm that I've written up there. So the polynomial ring mod out by the Chebyshev polynomial. Okay. And what we've seen right here is exactly what is known as a fusion ring. So this is a typical example of a fusion ring. So what is a fusion ring? If you're afraid of category theory, I urge you to look below. And if you're not afraid of category theory, look upwards. And in fact, unfortunately, at some point, I'll have to do the category theory. So I'll actually say things that correspond to the top part. Okay. So fusion category is just going to be a very simple thing. It's an abelian category, which is semi-simple. And it has only finitely many simples. Okay. So I said abelian category is very easy. And the interesting structure of this abelian category really comes from the fact that it is equipped with a monoidal structure. So you know how to do tensor product is the point. Okay. And this monoidal structure tells me that my monoidal unit has to be a simple object. And moreover, every object has to have a left dual and a right dual. And what I mean by that is that if I take an object and look at the functor corresponding to taking that object tensoring by it, that is a functor that goes from C back to C, that functor has to have both a left adjoint and a right adjoint. Okay, that's a lot of category theory. And if you're scared by that, again, a fusion ring is just the following data, right? It's just a 3D module with a particular kind of basis. We will just call B1 up to Bm, right? So every element in my ring is just given by linear combinations of those basis elements. And when I multiply those basis elements together, it has a nice integral property. What I mean by that is that if I multiply two basis elements together, you can rewrite it as a linear combination, right? By the fact that, by assumption that it's a basis. But these basis elements here are always non-negative integers. Okay, so that's the integral property that I was pointing out just now, right? And in some sense, like this is really the only most important piece of data that you have to remember about fusion ring. It's a ring with a particular fixed base choice of basis, where when I multiply two things together, rewriting them in terms of basis always only return non-negative integer coefficients. Okay, so let me give you some examples. If you're familiar with category theory, look on the left. Otherwise, just look at the stuff on the right hand side. So the fusion rings, the first one is just the group ring of a finite group G. Okay, so what are the basis elements? The basis elements are exactly your group elements. And of course, when I multiply two group elements, it always only returns non-negative integers when I rewrite them in terms of linear combinations of my group elements again, because it always returns me exactly uniquely one group element that it gives back. Okay. If you're a representation theorist, the representation ring of a group is always also a fusion ring. The basis is given by exactly your irreducible representations. Okay. And the two examples that the last one there is the examples that I given you just now. So this one right here. There's the polynomial ring modeled up by the Chebyshev polynomial. And the bases are actually the Chebyshev polynomials themselves. Okay. So in particular, you would be very intrigued to say that, well, this is a polynomial ring modeled up by an nth degree polynomial. Of course, your basis is going to be like 1, x squared, x cubed, x4 up to x to the power n, right? Yes, that is a basis, but it does not satisfy the integral property that I was talking about. But if you instead take the Chebyshev polynomials, so the zero Chebyshev polynomial, first one, second one, up to n minus 1 Chebyshev polynomial, those are still a basis, right? Because every mth Chebyshev polynomial is an mth degree polynomial. So all I've done is just doing some sort of change of basis. But those basis elements are better because now if I multiply those basis elements, instead, I always get non-negative linear combinations of Chebyshev polynomials. Okay, again, this is something that you can check at home, and it really just follows from the recursive relation that I was talking about just now. In the categorical term, it counts exactly how many copies of summands showing up. Exactly. It enumerates how many summands are showing up for each of the objects. Yeah. So in particular, again, if you're a category theorist, you can study representation of quantum group of SL2. You're enumerating the representations, and the summands that show up are exactly counting how many irreducible representations are showing up when you tensor two representations together. That's it. Yep.
What's cohesion? Some kind of intersection theory, cohesion, something like concern group, just think.
Let me think. I don't know if the Euclid SL2 case is, but in certain other examples of fusion categories, they will be. But I don't think for this particular example it is. But that's right. In certain cases, you can count intersection points in finite fields, if that makes sense. Yes. So in particular, you have to do representation of UKSL2, Q and roots of unity. You have to semi-simplify it, then you get a fusion category. Yep. Sorry, can you repeat that by finite rank algebras?
The finite rank algebra, like the Artesian rings.
I mean, the fusion rings would be, but I don't know about the fusion categories themselves. So they're slightly more, okay, let me just say a few things here. So fusion rings, I gave you a definition of fusion rings, right? And the way to go from fusion category to fusion rings is to take what is known as a grothendieck group. So what I mean by that is just saying that you multiply by exact sequences. Or actually, this is semi-simple, so it's even easier. So the relation on the grothendieck group is that you take isomorphism classes of all objects, okay? And you say that you write down the following conditions. Oh yeah, so then that's easy. So it's just a grothendieck group, and then the multiplication is just given by the tensor product, the monoidal structure. It is not true that every fusion ring comes from a fusion category. So there are more fusion rings than fusion categories themselves. And usually that kind of fusion rings, we call them the category-fiable fusion rings. So fusion rings that comes from a category. So I think when you want to realize them as like Artinian rings over Z with finite rank stuff, I think it only gives you fusion rings. Fusion category comes with slightly more data because you have to tell me what morphisms between objects are. And that's that extra thing. This one right here. So it's a finite rank Z. It's a finite rank Z module with a particular basis. Again, I want to really emphasize that you have to fix the basis as well. It's part of the data. It satisfies this integral property that I mentioned just now, and something that I did not talk about previously. This is, depending on the point of view, this could be a C-star algebra structure, this could be a dual structure, or Drazen inverses. Comes from a lot of things, but this is the data that it has to satisfy. It is also a hypergroup, if that speaks to you.
Any reason why some of the fusion?
What kind of reason would you wish, though?
Because it's integral already, right?
Yes.
It's a good sign.
Yes, it's integral already. It's a very good sign. I completely agree. And the problem is really the fact that you cannot upgrade it to a monoidal structure. So I didn't really say what a monoidal structure is, but basically it has to satisfy something called the pentagon equation. Basically tells you that, when you tensor x, y, and z, there's two ways to do it. You can first do x and y, you can do y and z. In the categorical level, the morphisms has to satisfy an equality condition, which is a stronger condition. But in the fusion ring case, you don't need to give me the morphism. You just say that they're equal. So going up that level sometimes has obstructions.
Associativity
with respect to morphisms. Yeah. In particular, if you're familiar with Cauchy cohomology, then Cauchy cohomology is what controlling. Okay. All right. So those are the examples. How am I going with time? Oof, that's already half an hour. All right. So the main thing that I want you to remember about fusion rings is two things. So the first one was like the integral condition, right? If I take two basis elements and multiply them together, it always return an element which can be written as linear combinations that only contains non-negative coefficients, right? That was the first thing. The second thing is this following statement. You can essentially think of fusion categories or fusion rings as vector spaces that has weird dimensions, but real number dimension. And I want you to agree with me on two things. If I tensor two objects together, my dimensions should multiply. And if I take direct sums of two objects, my dimensions should add. Okay. Once we're happy with that definition of dimension, and also the fact that objects should have positive dimension, right, non-negative dimension, then there's a notion of dimension that always works for fusion rings. And moreover, it is unique. Okay. I'm not going to tell you how to define this dimension, but rather just give you a hint. And the hint says that FPDIM, the F and P stands for Frobenius-Perron, the two names for Frobenius-Perron. So it's related to matrix theory, for Frobenius-Perron theorem, if you remember that. And that's how you will be using that to define this kind of dimension. But the point is that, first of all, it exists. Second of all, it is unique. So what this means is that if I go back to the examples that we've seen just now, if I'm just looking at my two standard rings, so either the representation ring of a finite group or the group ring of a finite group, the underlying dimension always works. Okay, the underlying dimension always works. And if I were to look at this example just now, so the one that comes from Chebyshev polynomials, then again, what do I need to do to assign numbers to these kind of rings? I'll have to tell you where xn minus 1 goes to, or this variable x goes to, right? There are tons of choices because every 2 cosine k pi over m is a choice. Only one of them will make sure that all of the Chebyshev polynomials actually return a positive real number. Okay, so if you send x to 2 cosine pi over m, all the Chebyshev polynomials lying between the 0 Chebyshev polynomial up to the m minus 2 Chebyshev polynomials, they will all have positive, they'll all be assigned positive real numbers. If you do any other 2 cosine k pi over m, it's no longer going to work. Okay. And the fact that 2 cosine pi over m showing up is in fact a general thing. It's in fact a general phenomenon. What I mean by that is the following. If you take any object in my category, or if you wanted the basis, if you take any basis element in your fusion ring, and then you look at this dimension map, and you check that if it's actually less than 2, it always has to be of the form 2 cosine pi over m, which is the number less than 2. Okay, and that's the unique occurrence. Okay, so as long as your object or your basis element has dimension less than 2, it always has to be of the form 2 cosine pi over m. Okay, and as we've seen from Coxeter theory, how do I represent Coxeter groups? Well, Jacques told us that we should use the number 2 cosine pi over m because that will always give you a faithful representation. And I'm claiming that actually you can instead use fusion rings or fusion categories because of this property right here. Okay, and what I mean by that is the following theorem. So let C be a fusion category and let R be the corresponding fusion ring. Okay, so the Grothendieck ring of that. And this is somehow a technical condition because we can't prove it if we just assume that R is non-categorifiable. So if R was just a fusion ring rather than a fusion ring coming from a fusion category, we don't know how to prove this. But we conjecture that's true. And the only thing, the case that we can actually prove are for fusion rings which actually comes from fusion categories. And the statement goes as follows. Play exactly the same game, right? For every vertex that shows up in your Coxeter graph, assign a basis element. And now the space that we're looking at is instead a free module over the fusion ring R. Okay, so previously it was a vector space of dimension equal to the number of vertices. Now it's a free module over the fusion ring R of rank equal to the number of vertices. Okay, and I'll define my bilinear form as follows. It doesn't even have to be a symmetric bilinear form, but the only condition that I'll assign are the following kind of things. If alpha s and alpha t, for the bilinear form between alpha s and alpha t, if s is equal to t, I'll put back the number 2, which was what we were doing just now. And I'll assign a negative of an object for my category otherwise. Okay, again, if you go back to the fusion ring picture, this just means that it's a negative linear combination of basis elements. Okay. And this assignment, so again, we play the same game. For every reflection S, we assign it to the reflection or an action that takes V and then return V minus bilinear form times alpha S. Okay. It's again a faithful linear representation, but now linear over the fusion ring R. And when is it faithful and when is it a faithful linear representation over R? If and only if the dimension of those objects that I've assigned, these objects right here, if and only if the dimension that I've assigned are actually 2 cosine pi over MST for the right MST numbers. Okay? Yes.
But not any real number, it has to be.
Exactly.
Do we know what? So only some spatial real number can be the dimension. Right?
Exactly.
And like infinity is also very suspicious, right?
Exactly. So for infinity, somehow every time when you use anything greater than or equal to 2, it will work.
Yeah, but there are different kinds of infinity.
Yeah. So if you go back, I like to say that it's not weird to like somehow do this Because if you go back to Coxeter groups, in Jakteet's representation, when it's infinity, you also put the number 2. But in fact, you can always change that number 2 to any number greater than or equal to 2. And the reason is that, okay, so let me give you an example. Think of the infinite dihedral group, right? So dihedral group where 2 things have no relations at all. Okay, that is usually an affine picture, an affine A1 picture. So it's a reflection along an affine line. If you change that reflection number, so instead of representing the bilinear form returning the number 2, change that to something greater than 2, you get a hyperbolic picture. The cone that you get is actually something that's a proper cone rather than a half plane. Okay. So you're right. The funny thing somehow is the fact that when it's less than 2, it's always of this form. So we can actually use this number. And when it's greater than or equal to 2, we no longer have any control. And this is just, all you need is just to make sure that it's actually greater than or equal to 2. Yes.
I mentioned lesson 2, you only have a kind of a sign kind of thing.
Yes.
This reminds me of really some kind of sub-factor theory.
Yes, it is.
Are they the same thing? Or?
Yes, yes. Fusion categories, tons of examples of fusion categories. In fact, interesting fusion categories all comes from sub-factor theory. But that's another connection. So in fact, the fusion rings that I showed you just now, the one that modeled out by Chebyshev polynomials or UKSL2, those are type A sub-factor theory. If that means anything to you.
TLJ, right?
Yes, it's also TLJ stands for temporally lead Jones, and that Jones is the Jones that you're thinking about who studies sub-factor theory and got a few medals out of it. Okay. All right. How am I doing on time? Pretty badly, but okay. So let me just quickly describe this then. So not only that, every such assignment actually gives you a faithful linear representation. And in fact, given any Coxeter graph, there's always one way to realize it as a linear representation over a particular fusion ring, a choice of fusion ring. And what I mean by that is just taking the Chebyshev polynomial rings, fusion rings that we've seen just now, and do the tensor product appropriately. Okay, so the statement is just that every Coxeter group has a faithful linear representation over a fusion ring R for some appropriate fusion ring R. Okay, all right. So let me now go to the second picture then. So I want to first remind you how quivers and wall groups, so a particular family of Coxeter groups, are actually related. So a quiver is just going to be an oriented graph. So take a graph, put some sort of orientation in it. By that, I just mean take your edges and then make them arrows. Okay, so that's a quiver. And here are some examples of quivers. And for my talk, I'll just assume that my quiver will always be finite, meaning only finitely many vertices, finitely many edges. And for technical reasons, I'll just assume that they are also acyclic. So there are no loops along my quivers. Again, just for technical reasons. You can always drop those if you really want to get into the details. And let me quickly remind you what a representation of a quiver would mean. Right? So representation of a quiver just means that to every vertices I attach a vector space, and to every arrow I'll attach a linear linear transformation, or a linear map between the two vector spaces. Okay, so that's just what it means to be a representation of a quiver. If you're more into algebra, then you can write down the path algebra of this quiver, and then these are exactly the modules over the path algebra as well. That will also work. Okay. So morphisms among representations are again something similar. You just have to give me a map between each of the vertex. So for each vertex, I've already attached a vector space, and the morphism between representation is just a map between the vector spaces, such that these diagrams actually commute. Right. So for each arrow, you actually have a commutative diagram. Okay. So and the statement is that this forms an abelian category. I didn't tell you how to do direct sums, but you can imagine how to do it. You just take direct sums along all the vertices, and then along all the arrows, you also take the direct sum of morphisms. All right, and this forms an additive category, and you can check that it is in fact an abelian category. All right, let me do some examples. Let's take this quiver, the A2 quiver with one particular orientation. And these are examples of representations, right? For each vertex, I'm attached some sort of vector space. Most of them are one-dimensional, except for the very last one that I have a two-dimensional vector space on the first vertex and a one-dimensional vector space on the second vertex. Okay? And for morphisms, we have to be slightly careful. I can't just write down any maps, but I have to make sure that my maps actually commute, right? So in particular, for example, for this one right here, I could have written a non-zero map between these two vector spaces, right? But if I write down anything that's non-zero, this will give me something non-zero, but this will be zero all the time. So the only morphism between this representation and this representation, in fact, is the zero morphism and nothing else. Okay. And now let's look at this example instead. All right, the second example, the very last one that I had just now. I started off with a representation that looks like this. My claim is that you can always decompose it, right? And what I mean by that is that you can write down an isomorphism, right? So this is an isomorphism, this is an isomorphism, and what I've written down is actually a commutative diagram. Therefore, it is a morphism of representation. And for this guy below here, it looks like a direct sum of two representations, right? Because I have a map from the first copy of K as the identity map into K, and for the second copy, it's just a zero map, which is this notation right here. Okay, and therefore it really is a direct sum of two representations. This is what we call a decomposable representation, right? What I mean by that is that this representation, although at first it doesn't look like it's decomposable at the very top there, up to isomorphism, it is in fact a decomposable representation. And what you can check is that actually, up to isomorphisms, there are only three indecomposable representations, which are these three that are written up there. Okay. In particular, if any of your vertex has a vector space of dimension greater than or equal to 2, then it has to be a decomposable representation. Okay. And if you count the number of indecomposable representation, what Jacques again made the observation is he says that, well, this number actually is equal to the number of positive roots that shows up in the wild group theory. And what I mean by positive roots is just the following picture. So you can't quite see the triangle, but you should be looking at the triangle right here. And the positive roots are exactly just under reflections. All of the under reflections, the orbit under reflections of all the basis elements right here. You have 3 pointing out here and then 3 pointing downwards. And the positive ones are the ones that lives on the particular upper half space. All right? And it looks like there's a bijection between the indecomposable representation and the positive roots just by counting how many dimensions of vector spaces showing up in the first vertex and in the second vertex. Okay? So in particular, if I just label this by alpha 1, label this by alpha 2, I get that this is alpha 1 plus 0 alpha 2. This is 0 alpha 1 plus 1 copy of alpha 2. And this is alpha 1 plus alpha 2. Right? And that recovers exactly the positive roots of my dihedral group of the triangle right here. And this is what Gabriel, first proof of Gabriel in, I think, the 1980s. And then also first time from Paul and Moreff giving a more conceptual proof using reflection functors. And it goes as follows. Again, we see some sort of AD classification here. And it states that any quiver Q, again, including an irreducible, so connected quiver Q, any connected quiver Q has finitely many indecomposable representations. If and only when I forget the orientation, it looks like one of these diagrams again. All right? We start off from something that looks completely different. We're doing quivers, we're doing representational quivers, but we're back to the same kind of diagrams again. Right? And moreover, what you can prove is that there is a one-to-one correspondence between the indecomposable representation and the positive roots of your wild group, or the Coxeter groups of ADE types that shows up here. Okay? And my question then is, what do we do for the other Coxeter groups? Even in the simplest case, right? Just for positive roots of Coxeter system that looks like this, right? So for dihedral groups of pentagon. In this case, we have exactly 5 positive roots. Okay? And is there a quiver theory that somehow corresponds to this? Well, my claim that it actually does. And the point of view is that instead of taking representations valued in vector spaces, we should take representations valued in fusion categories instead. Okay, so previously you remember that what is the representation of a quiver. To every vertex, we attach a vector space. And to every arrow, we attach a morphism between the two vector spaces, which are linear maps. Okay. Now, fix in state a fusion category. Okay. To every vertex, we will attach an object in the fusion category. And to every arrow, we'll attach a morphism in the fusion category. All right. So if my fusion category was just back to the simplest fusion category possible, which is the category of vector spaces, you recover the definition of a representation of quiver. Okay. So here's a more precise definition. I'll first enhance my picture of quivers, and from now on, I'll allow also my arrows to be labeled by certain objects in my fusion category. Okay, so a fusion quiver is just a quiver, so your usual or ordinary quiver, but now arrows are allowed to be labeled by objects in my category. So it just looks like something like this. And if I take a representation, I do exactly the same thing. On each vertex, I attach an object. And the only data that I'm changing right now that is slightly different from what we've seen just now is that given an arrow, when it's labeled by an object pi alpha, I will twist it first using the tensor product that exists in my fusion category. I'll twist it by the monoidal structure and then take the map. Okay? If you've seen species before, this is very similar to species, but otherwise you should think of this as this guy here is counting how many arrows you're using. Okay, if this guy has dimension 2, it's almost saying that you have 2 copies of BI mapping to BJ instead. And this one here is twisting it by dimension of your object equal number of arrows. Okay, so that's the main data that's actually different. That's the main structure that we're using from the monoidal or the tensor product structure of our fusion category. Okay, and morphism works exactly the same way. To every vertex, I give you a morphism that goes between the objects, and the commutative diagram has to still hold, right? And the main difference is that previously I only have these because these tensor products here don't quite exist. Now I'm still asking for the same commutative diagram where I'm not allowed to touch this part, the tensor product part right there. So it has to be Fi tensor identity and Fg on the other side. And you can do this same yoga. You can check that, you can actually check that this again forms a category, forms an additive category, and moreover, because my fusion category was actually abelian, it is also the category of representations is again an abelian category. Okay, let's look at an example. So let me take my fusion category to be the Fibonacci category. Okay, I didn't really get to say too much about it just now, but I'll just tell you what this category looks like. This category has exactly 2 simple objects. One that I'll call 1, because you should really think of it as categorified 1. And the other one I'll call tau, which you should think of it as a categorified golden ratio. Okay? And what I mean by that is that when I take tensor product between 2 objects, if I take tau, tensor by tau, it returns 1 direct sum tau. Okay? And on the fusion ring level, all this says is that it satisfies x squared equals 1 plus x. All right? And there's only 2 numbers that satisfy this equation. One of them is the golden ratio, and the other one is the conjugate. The conjugate is not positive. Okay? So the dimension of this object is the golden ratio. Hence the name Fib, because it's called the Fibonacci category, or sometimes also the golden ratio category. Okay? So let's take this as our fusion category. And let's look at the example, which is this fusion quiver right here. All right, so it's just a quiver that looks like the A2 quiver that we saw just now, but now my arrow is labeled by this golden ratio object tab. Okay, and what does it mean to take a representation in this fusion category? Well, again, to vertex, I just give you some sort of object. So here I've written down some choices. Some of them are 0, some of them are 1s, and some of them are this object tau, that is the golden ratio. And similar for the other vertex, and I have to write down a morphism that actually makes sense. Okay, in particular, let's see. If I take 1 here, then this is 1 tensor by tau, which is tau, and this is again tau, then there's a morphism between these 2 things. If I replace tau by 1, tau, this gives me an object tau here and an object 1 here, and those 2 are different simple objects. therefore no morphisms between them. Okay, by assumption, right? Because they are semi-simple categories. Okay, and so these are possible choices. What is new that doesn't exist in category of representation of quivers back then is that you can always tensor from the left-hand side. Okay, what I mean by that is that now, given these set of representations that I have right there, I can always just tensor everything on the left-hand side. Right, so now every object now, instead of being 0 is tau times 0, instead of 1 is tau times 1, so on and so forth. Right, and this is functorial, so I know what to do on morphisms as well. Okay, this gives me a new set of representations. Right, the precise term for this is that this is actually what is called a module category over the fusion category. But what I want you to keep in mind is just the fact that there is an action of the fusion category from the left-hand side, just by tensoring on the left-hand side. And that gives me a new set of representations instead. And the claim is that actually, these are all of the indecomposable objects. So again, technically, there's actually 10 indecomposable objects in this category. So there's actually 10 indecomposable representations. But up to the action of tau, there's only 5. And the picture looks something like this. These 5s here are exactly your positive roots. Again, you play the same game. Call whatever that you have here, number of copies of alpha 1, or whatever they have there, number of copies of alpha 2. And by converting this to the grossity group level, you get exactly these 5 objects there. And tensoring by tau is just as if you're extending the length by the golden ratio number. And that was it. Okay, so up in some sense, you should think of this as up to the orbit of my fusion category, up to acting by objects in my fusion category, there are exactly 5. Right? And that is the theorem. So I'll just skip straight to this because of time constraints. The theorem that Ben Elias and I proved sometime last year, I think, I can't remember which year anymore, is the following theorem. If I take the category of representations of fusion quiver, and again, it has finitely many indecomposables, if and only if the underlying graph looks like a Coxeter-Dinkin diagram. Okay, I didn't tell you how to replace objects into these numbers right here, but let me just quickly say that basically you just look at this dimension. If it's less than 2, it's of the form 2 cosine pi over m, pick that m. If it's greater than or equal to 2, it's going to be infinity. Similar to the yoga that we saw just now in the representation level. Okay, and it's going to be having finitely many incomposables if and only if by convergence to this kind of things, this kind of graphs, it looks like a Coxeter-Dinkin diagram. And it extends Gabriel's theorem from the 80s that tells you that only ADE diagram shows up. Here you get everything, including the weird non-crystallographic Coxeter groups that shows up here as well. Okay, and moreover, the theorem that we saw just now from Gabriel's theorem, saying that there's a one-to-one correspondence between positive roots and indecomposable objects, also has a similar form. It basically says that the set of positive roots and indecomposable representations up to the action of the fusion category, up to tensoring on the left-hand side, are in one-to-one projection again. Okay. All right. Okay, so in my last minute, maybe let me just quickly say what we can do with this. Okay. So in the theory of Coxeter groups, and in particular in the theory of braid groups, one is interested in the lifted version of Coxeter groups. And let me just show you this particular example right here. So you stare at this group presentation. It's exactly the same as the Coxeter group presentation, except I've thrown away the involution property. I've thrown away S squared equals 4. Okay. And these kind of groups are called generalized braid groups. Sometimes it's called Artin-Titz group, because in the particular case, it gives you exactly the braid groups right here. Right, so in particular, if I drew my diagram as the A2 diagram, you get exactly this relation, these braids, which satisfy STS equals TST. And that's exactly the braid group. And these kind of groups can be really realized as fundamental groups of certain spaces called the complexified hyperplane column, which I won't spend too much time about it. But basically, you should think of it as, take the representation that you saw just now. There are certain lines that are the reflection lines that you saw. right? In the dihedral picture especially. Complexify that space and then take the fundamental group, right? Because if you just remove the lines in the real space, that's a disconnected space. But if you first complexify it and then remove complex hyperplanes, now you have monodromies, and pi1 of that space is interesting. And it gives you exactly great group up to module modding out by some quotient. And the k pi1 conjecture basically says that this space is the classifying space of my group. Okay, so it says equivalently, it says that this space has a contractible universal cover. Right, this is the old conjecture. It was first proven by Deligne for all finite Coxeter groups in 72. Later on, the first breakthrough was in 95, proven by Charney and Davis. And very, very recently, only we were able to do the affine types. Okay, so just Coxeter linking diagrams with one vertex extended. And that was it. And that was proven in 2022 in an Inventionist paper. And since then, Huang and Attel has been able to prove for some sporadic cases every now and then. But sorry, you can't see this rate. But the point is that this is still largely open in general. We only know for certain families, if you write down a random Coxeter graph, most likely there's a high chance that it's actually going to be open. Okay. And there's in fact a categorical approach that me and my supervisor and other people like Michael Weems and so on have been trying to approach this problem. And it's using the theory of Tom Bridgeland's space of Bridgeland stability conditions. So what we're going to do is the following. We first construct a categorical action of the break group on a triangulated category, whatever that means. And a strong result by Bridgeland tells us that this triangulated category always comes with a complex manifold called the space of Bridgeland stability condition. Okay. For the correct triangulated category, it turns out that this is a covering space. It's a covering space of the complex hyperplane, complexified hyperplane complement that we're interested in. And as far as we can tell, space of stability condition has always been contractible. Okay, in the sense that if you look at its particle connected component, all the examples that we computed has been a contractible component. So if you prove that STAB is contractible, it comes for free that this space is not just a covering space, but also universal cover, because contractible implies simply connected. And moreover, you prove the k pi1 conjecture. So if you like, by starting this picture right here, you have generalized k pi1 conjecture into an even stronger conjecture of Bridgeland, which says that stability conditions should be contractible. And that would give you a unified way of proving k pi1 conjectures for all cases. Well, if we have done that, then I wouldn't be standing here telling you about this whole story, because we would have solved a very, very strong problem. But there are positive directions. First proven by Chu and Wolf, and also August and Wims in a different context, that in fact, for ADE graphs, these are all, the stability conditions of these triangulated categories are in fact contractible. And I just want to emphasize that this is, although I write down theorem, this should really be a corollary. Both of them prove for a large class of triangulated categories, satisfying something called tilting discreteness or tilting finite, have contractible space of stability condition. Just turns out that these triangulated category that we're interested in has this kind of properties. Okay, and this would imply the k pi1 conjecture, and in fact it does, and it gives a new proof of the k pi1 conjecture as well. So in the joint work with Tony Licata, we generalized this whole picture into all Coxeter groups. So previously we will only be able to do it for wild groups again, because you want to use some sort of quiver theory to construct this kind of triangulated category. And when you use quivers, you only get wild groups. We were able to do this by generalizing using the structure, the fusion quivers that I showed you just now, studying something called the pre-projective algebras or the zigzag algebras associated to them, and construct the triangulated category and study the space of stability conditions. There's a technical detail here that I'll just quickly go through, which says that actually the whole space of stability condition is not the correct covering space, but it's just the fixed points with respect to the fusion category action. So what we've defined is that there's actually a closed submanifold of the space of stability condition, which are basically fixed points if you think of the fusion category as a group. That is always a closed submanifold, and we prove that this is a covering space. And we were able to prove a lot of things about what is actually the whole space of stability conditions as well, what kind of covering it is. It just covers a different hyperplane complement, and it also gives you like embeddings of hyperplane complements as well. And again, the positive answer is that if gamma was a finite type Coxeter groups, then this covering again is universal and moreover contractible, hence K-pi1 conjectures. Okay, so I have gone out of time, so I will just stop here and throw you a list of things that I've been thinking about, and also what kind of problems you can use from this kind of construction. Thank you.
Okay, thank you for the talks. Any questions from the audience?